You are welcome to the class. We want to continue our discussion on partial differential equations. I told you that partial differential equations stem from the knowledge of partial derivatives. For instance, when we have something like y is equal to y into x comma t, so this is telling you that there is a dependent variable y that is connected to two independent variables x and t. So let us go specific. For instance, we have something like y is equal to s squared plus t squared. So this is a specific example of what y might look like. So y is equal to s squared plus t squared. So the expression is just an example. So it might be more complex than this or simpler. So it doesn't mean, for instance, if you want to find dy dx now, dy dx, that's the partial derivative with respect to s, is equal to 2x, and dy dt is equal to 2t. So from this knowledge now, we have been able to know the derivative of y with respect to x based on this expression we are given. So, and we have been able to know the derivative of y with respect to t based on this expression we are given. So our dy dt is equal to 2x because we are treating t as a constant, and our dy dt is equal to 2t because we are treating x as a constant. So having known this now, we can form a lot of partial differential equations from this knowledge that we have. For instance, I might decide to say my partial differential equation is dy over dx plus dy over dt is equal to 2x plus 2t. So, and you see that it is true because our dy dx is equal to 2x and our dy dt is equal to 2t. So it is true that our dy dx plus dx is equal to 2x plus 2t. So this is a correct equation. So we can see write this equation like this: dy over dx plus dy over dt minus 2x minus 2t is equal to 0. So dy dx plus dy dt is equal to 2 minus 2x minus 2t is equal to 0. So this is a partial differential equation. This partial differential equation can be written as f into x comma t comma dy comma y, because we must have a dependent variable. Let me clean this one. So we must have for y, which is a dependent variable, then dy over dx, then dy over dt, so which is equal to 0. So we have our x, we have our t here, we have our x here, we have our t here, so we have our y, which is in the partial derivatives. So because if you don't have y, you cannot have the y dx and the y dt. So then we have the y dx itself, the y dt itself, everything being equal to 0. So this is how a partial differential equation looks like. So assuming now that we did not know all this expression, we didn't know this expression, and we are given this partial differential equation here now. So and we are asked to find solutions to this partial differential equation. We must know that this one that I wrote here is a solution to the partial differential equation that we formed here. So it's one of the solutions because a given partial differential equation has more than one solution. In sometimes it might have an infinite number of solutions. So you must know that it is not that only this expression satisfies this partial differential equation. We might have some other expressions that can satisfy this type of partial expression. So when you are given a partial differential equation, you have to find the solution. You should bear it in mind that you can have specific solutions that are infinite in number. You might have many of them. So satisfying this partial differential equation that you are given. So based on this, that is how partial differential equations are formed. So a partial differential equation is a function that consists of independent variables, a dependent variable, then derivatives of different order. It might not be one first order derivative only. It might be second order, third order, and so on and so forth. So they are connected inside a function, and that function is equal to zero. So that is the general form of partial differential equations. So you must know that partial differential equations are very, very useful. They are useful in phenomena. For instance, world population or population of a community can be modeled using partial differential equation. For instance, we are considering the economic condition as an independent variable. We are considering the birth rate as an independent variable. We are considering the death rate as an independent variable. So you are having three independent variables. So you can connect it to the population growth. So and use your partial differential equation to model it so that you can predict future population for that community or that country. So partial differential equation has a lot of benefit in modeling. So it is very, very useful. So but you should know that these partial differential equations are of different class. We have classification for partial differential equation, classifications, classifications. So classification, you can classify partial differential equation based on linearity. Linearity. So some partial differential equations are linear, while some partial differential equations are non-linear. For instance, the last partial differential equation that I discussed, this one that I discussed, this one is a linear partial differential equation. It is linear because the coefficient of x, the coefficient of the y dx is 1. The coefficient of the y dt is 1. So 1 is a constant. So y does not depend on 1. It does not depend on this coefficient. So the coefficients are constant and they do not vary with y. So that is why we say it's a linear. Any partial differential equation that looks like this is a linear partial differential equation. For instance, we have a 2 dy over dx plus 3 dy over dt is equal to x. So assuming we have something like this now. So this is a linear partial differential equation. But if I have something like x dy over dx plus maybe 3t dy over dt is equal to 0. So this is another partial differential equation. So you see that y is dependent on x, y is dependent on t, and we have x as coefficient of this one. We have y as coefficient of this one. No, we have x as dependent coefficient of this one, and we have 3t as coefficient of this one. And y is dependent on t, y is dependent on x. So in this case, this is a non-linear differential equation. Because for you to call a differential equation linear, it must satisfy a condition. What is that condition? So the condition is LU is equal to 0. Here your L where your H stands for the derivative and your U stands for the the change in the dependent variable. So your LU is equal to a 0. Your L is equal to, maybe for instance, in this in the previous differential equation, this differential equation of this one, the first one that we have here, we can write it like the L is equal to our 2 over the x 2 over dx plus uh, what again, 3 over dt, 3 over dt. So and our u will now be equal to the y. So and everything is equal to 0. If you look at it, our u is the y, and this is 2 over dx, this is 2 over dt. Our dy will be moved out. Our dy will now become u now, and our L will now become 2 over dx plus 3 over dt, which is equal to, everything is equal to x. So in this case, you see that it is easy to express our expression as a LU, as a LU is equal to, maybe is equal to is equal to x. Let me say it's equal to x in this case. So we were able to express our given partial differential equation. This given partial differential equation, we're able to express it as LU. So and is equal to x. So because it is equal to x here, but it is not possible. It is not possible. It is also possible to do it in this way. This is also a linear partial differential. This is a linear partial differential equation, but this is not linear. So this is not a linear partial differential equation. So this is a linear partial differential equation, but this is not linear because the coefficient of the y dx and the y dt is equal to 0. So partial differential equations can also be classified based on homogeneity. Homogeneity. So there are some partial differential equations that are homogeneous and there are some that are non-homogeneous. For you to say partial differential equations homogeneous, then you have something like the y over dx plus maybe let me say t dy over dt is equal to 0. So this type of partial differential equation is homogeneous because everything is equal to 0 here. Everything is equal to 0. It is non-linear because you have an independent variable as coefficient to the y dt. So, but it is homogeneous because it is equal to 0. For instance, we have something like the y over dx plus t dy over dt is equal to x. So this is not homogeneous though. This is not homogeneous because it is not equal to 0. It is equal to x. So it is not homogeneous. If you have something like the y over dt plus the y over dx minus x squared is equal to 0. So you can see now this one is linear, but it is not homogeneous. So it is linear, but it is not homogeneous because we are going to move this x squared to this side. So you now have the y dt plus the y dx is equal to x squared. So it is not homogeneous. So I've classified partial differential equation based on linearity. You have some that are linear, you have some that are not linear, you have some that are homogeneous, you have some that are not homogeneous. To be able to differentiate all those things, you should be able to classify a given partial differential equation as a homogeneous, non-homogeneous, linear, non-linear. So we have different orders of PDEs. So partial differential equations are of different orders. So you should know that. For instance, if you have something like y is equal to let me see the y dx. Let me use let me give use an example of a partial differential equations. For instance, if we have something like the y over dx plus the square y over dx over the t square is equal to 0. So this is a partial differential equation of order 2 because the derivative of highest power is the square y dt square. So the order of this one, the order is 2. Order is 2. So the order of this partial derivative is 2 because the square y dt square has the highest power among the partial derivative that we have here. So the one that has the highest power will be the order of the partial differential equation. So for another example, if you have dy dx plus dy dt is equal to 1. So this is of order 1. Order is 1. So the order of this one is 1. So that is how the order of a partial differential equation is determined. So as we continue, we are going to be discussing how we are going to be dealing with each of those order and each of the other classifications that we have discussed earlier. So in continuation, you must know that we have some standard partial differential equations that researchers normally employ in modeling their uh, their their experiment or in modeling whatever they want to model in terms of natural phenomena. So number one, we have what we call transport equation. Transport or advection equation. Advection. Transport or advection equation. So it's a standard partial differential equation that we normally borrow in modeling something. All those ones they have devised ways of solving them. So that is why they call them standard partial differential equations that one can borrow when you want to model whatever you want to model. Example of them is transport or advection equation, and that one looks like the y over dt, the y over dt, the y over dt plus c, the y over dx is equal to 0. So anything that looks like this, where c is a constant, so you have your dy dt, you have your dy dx. So you should know that your solution consists of functions that have t and x as independent variables. So this is a transport or advection equation. So when your partial differential equation looks like this, you should know that the method of transport or advection equation can be applied to solve your partial differential equation. Another one, number two, we have what we call wave equation. Wave equation looks like the square y over dt, the square y over dt is equal to k, let me say k, the square y over dx square. So wave equation looks like the square y dt is equal to k, the square y over dx square. So this is dt square. So you shall know that your k is greater than 0, so your k is greater than 0. So another one is diffusion equation. Diffusion equation. So that one look like the y over dt minus the square y over the x square. The x square is equal to 0. So that is diffusion equation. So there's another one, Burger's equation. Burger's equation. So Burger's equation looks like the y over the x plus u, or let me say y plus y, the y over dt, So or you say the y dt plus y the y dx, Let me clean this one and write it. So clean this one and write it. So the equation looks like the y over dt plus the plus y, the y over dx is equal to 0. So is equal to 0, 0. So all these ones are standard equations, standard partial differential equations that we can employ their solution in solving our solution. So you should look whether your partial differential equation looks like this one or it doesn't look like this one. If it looks like any of these, you know that you are going to employ the method they use to solve all these kind of equations to solve your partial differential equation. So when we get to solution of partial differential equation, so we should be able to talk more about all this. Thank you very much for being part of the class. If you have any questions, you can relate to me. Thank you very much.